Okay, so let's go over this. So we'll do we'll work our way down, and so we'll do 3.4 first. And so this is about molarity, and so it asks you how many grams of lactic acid. It gives you the molecular formula. Lactic acid are in a half a molar solution of lactic acid. And then it gave you, these here are the atomic masses for carbon, hydrogen, and oxygen. And so the first thing you need to do is to figure out the molar mass of lactic acid. So there are 3 carbons in lactic acid. Each one of those have a mass of 12, so therefore there's 36. And then there are 6 hydrogens. Each one of those have a mass of 1, so we add 6 to that. And there are 3 oxygens, and each one of those have a mass of 16. So we add 48 to that. And so then we get 90. And what this tells you in terms of molarity is that if you measure out 90 grams, which is the molar mass of lactic acid, that's 1 mole of lactic acid. So that's 6.02 times 10 to the 23rd molecules. And so then how that relates to molarity, remember molarity is grams per mole. So if you put 90 grams into 1 liter, you have a 1 molar solution, because you have 1 mole in that 1 liter, so you have a 1 molar solution of lactic acid. And so this is asking you, though, not about 1 mole, this is asking you about 0.5 molar solution. So therefore, to have a 0.5 molar solution, you could take 45, you have to take half of that. All right, so that 0.5 means a half of a mole. So 90 grams is 1 mole, so 45 grams into the 1 liter. Does that make sense? Okay, and so 45 grams in 1 liter is a 0.5 molar solution. So that's what I'm going to do here. Now the next one, there's a lot of questions this morning about the next one with making a salt solution, and a couple of things here is making 2 liters of a 2 molar salt solution. And it gave you here again the atomic mass here, and did anybody notice, anybody look up Cl, did anybody notice that there's actually, this is a typo, anybody notice that? Oh, doesn't matter. It's actually 35.45, I don't know, the publisher made a mistake, but I want to make sure that somebody can calculate it the other way. All right, so what you're going to do is you get the molar mass, and so there's only 1 sodium and 1 chloride, so therefore we take 23 plus 34, and that's going to give me 57, right? So that's the molar mass of sodium chloride. So what, again, remember 57 grams in 1 liter would be a 1 molar solution, but what is it asking for? Sorry, this is like focusing, you know. It's asking for a 2 molar solution and 2 liters of that 2 molar solution. So does anybody have an idea what we would do? Go ahead. No, Scott.
Multiply the 57 by 4.
Yeah, we multiply the 57 by 4, and so think about this like, so 57 grams in 1 liter makes a 1 molar solution. So if we doubled that, all right, to make a 2 molar solution, that would be, so you need 114 grams per liter to make a 2 molar solution. But we need 2 liters of that, so then we multiply it by 2 again, so you would need 228 grams in the 2 liters. Does that make sense? Okay. So we multiply that by 2, and then we multiply that by 2 again to get 228 grams in 2 liters. And that gives you 2 liters of a 2 molar. Okay. Let's do the interactive question 3.5. A lot of questions on this too. This this year I have quite a few people that didn't quite get to the in-depth of pH and chemistry that I've had in years past, so I just want to make sure you all understand this. So let's look in the reading, a couple of things. It says in an aqueous solution, the product of the H plus and OH negative concentration is constant at 10 to the negative 14. And so it gives you an example down here that if the OH negative concentration is equal to negative 10 molar, then the hydrogen ion concentration will be equal to 10 to the negative 4 molar, and if you multiply these together, you get 10 to the negative 14, so that's constant. And so that's another piece of information. And then the next thing is this equation here. pH is the negative log of the hydrogen ion concentration. So what does that mean? So when we say pH is negative log of the hydrogen ion concentration. So let me give you an example. Let's say the hydrogen ion concentration is negative 4. So 10 to the negative 4. When you figure this out and type that into the calculator and took the negative log of that, you get the number 4. And so therefore, when we say a pH of 4, it really means that the hydrogen ion concentration is 10 to the negative 4. All right, so that's how that's related. So how does that relate to the pH scale in terms of the numbers? So what does 10 to the negative 4 hydrogen ion concentration mean? So if you have, let's say, a pH of 4, when we talk about the hydrogen ion concentration as 10 to the negative 4, what that means is it's 0.0001. That's 10 to the negative 4. You move the decimal place over, all right, 4 places. So that's what we're talking about there. And so if we relate that to, let's say, a pH of 3, a pH of 3 has a hydrogen ion concentration of 10 to the negative 3. That is 0.001. Notice here the difference here. It's a tenfold difference. So a pH of 4, is a pH of 4 more acidic or basic than a pH of 3? More basic, right? So this is more basic in relationship to one another. And so what does that mean in terms of the hydrogen ion concentration compared to the pH of 3? So that hydrogen ion concentration be higher or lower? For pH of 4 versus the pH of 3. Go ahead, Colby.
When you first one, the hydrogen ion concentration is lower.
All right, yeah, for this one here, this one will have a lower hydrogen ion concentration. This one is more acidic than pH of 4, which means that it would have a higher, I guess I should put the brackets, higher concentration. And if you look here, 0.001 or 10 to the negative 3, is that a bigger number than 0.0001? Absolutely. And so that's why the pH, that's why as you go down the pH scale from 4 to 3 to 2 to 1 and so on, it becomes more acidic because the concentration of hydrogen ions is higher. All right? And so it's a tenfold difference there. So a pH of 3 has 10 times as many, 10 times the concentration as a pH of 4, and a pH of 2, 10 times as a pH of 3, and so on and so forth. All right, so that's what some of this stuff means in here. So let's relate this to this table here. So they give you, for the first one, lots of information. It's acidic, it's a pH of 3. This column tells you, these two columns relate to one another. If it's a pH of 3, that means it's 10 to the negative 3. The H plus concentration. And remember then the OH negative and the H plus need to equal 10 to the negative 14, which it does. So in here they only give you, the second row only gives you one piece of information. The hydrogen ion concentration is 10 to the negative 8. That tells you that it's a pH of 8. It also then should tell you that the hydroxide ion concentration should be 10 to the negative what? 6, because this should equal 14, and this is a basic solution. Hydrogen ion concentration is lower than the dark side. All right, then they only give you the OH negative concentration at 10 to the negative 7. We can figure that out. 10 to the negative 7 for H pluses to equal 10 to the negative 14. From the H plus, we know that that's a pH of 7, and in this case here it's neutral, so it would be pure water. And then lastly, it gives you a pH of 1. So the thing that it tells you about is that the hydrogen ion concentration is 10 to the negative 1. That means the hydroxide ion concentration is to be 10 to the negative 13. And this is acidic. All right. So that's kind of how you think through that. Any questions on that? Okay. All right, so then let's look at interactive question 3.6. So this is with the carbonic acid buffer system. So remember a buffer, what does a buffer do? Resists changes in pH. So therefore, whatever's happening to the solution, it wants to put the solution back to where it was. So A says when the pH of a solution begins to fall. So if the pH, that's the pH number, like pH 2 to pH 1, so it's going from, it's falling. So it's becoming more what? It's becoming more acidic. So I'm going to kind of just go through the thought process here. It's becoming more acidic, which means that what is happening to the hydrogen ion concentration in the solution? Is it going up or down? It's going up. So H plus concentration is going up, which means then that what do we want to do?
Let me be in your snapshot.
We want to lower it, right? We want H pluses out of solution, to take H pluses out of the solution. So how do we do that? Which direction would take H pluses out of solution to bring it back to where it was at? To the left, all right? Because if it goes to the left, this H plus is going to bind to the bicarbonate ion, and it's going to form carbonic acid, and therefore H pluses will be taken out of the solution. So this one goes to the left here. And then, so on the flip side, when the pH rises above normal, the same thought process, the solution is now more basic, which means then the H plus concentration is going down. So what do we want to do? We want the H pluses, we want the H pluses to go up, and so to combat that, and so which direction makes the H pluses go up or releases H pluses? To the right. All right. So if it goes to the right, this is going to break down into the bicarbonate and release H pluses. All right. Any questions on that? Okay. All right. So then let's look at the next one. This one here. Okay, so these guys, the first three, let's just go over this. These are all isomers. For our test, these are three different ways that you could get isomers, structural, geometric, or enantiomers. What they have, all of the types of isomers, what they have in common is they have the same formula, but they're put together differently. And so these are just three different ways that they could be put together differently. For our test, I told you guys this in the notes, for our test, you should just be able to recognize if they're isomers. I will not ask you if it's a geometric, structural, or so on. So you won't have to distinguish between these three on the test. You just have to be able to look at molecules and say, okay, yes, these are isomers. So let's look at the different types of isomers. So structural was A and C, and I know a lot of people have questions on these. So A and C. So if you look at the atoms of molecules A and C, here they have the same phosphorus, carbon, hydrogen, and oxygen. They have the same formula, but they are put together differently. You can see that the location of the double bond in the end versus the middle, and so on. So they have a different structure. And so those are two isomers of one another. For geometric isomers, one way to have isomers is different chemical groups on different parts around the double bond. And so in this case here, this is B and F for the geometric. And so let's look at these guys. These are also isomers because if you look here, they both have a carbon-to-carbon double bond. But what makes them different, they both have two CH3 groups and two H's coming off of those carbon-to-carbon double bonds. But we look at the CH3 on opposite corners, on opposite sides of the double bond versus on the same side. And no matter how we arrange these guys, they will not, we can't get them to look alike without actually breaking the bonds and reforming them. So that's another way to have isomers. So on the test a week from today, like if I have examples of this, you should just know that B and F are isomers and A and C are isomers, but you don't have to tell me that for geometric. Okay, all right. And then 3 can have enantiomers. In hindsight, I probably would have told you that you didn't have to do this question. Enantiomers, what that means is they have an asymmetric carbon, which means that it's bonded to 4 different groups of atoms. So we learned about enantiomers in terms of mirror images of one another. So remember, if this is your carbon right here, carbon can make 4 bonds. So let's say we have group A, group B, group D, and group E here. And so if we have another carbon over here, remember mirror images, the top and the bottom stays the same as the left and the right. So if we switch this and here, these guys are mirror images of one another. And so this is an asymmetric carbon atom, meaning that it has 4 different groups of atoms here. So let's look at the ones that's the case. There are 3 of them. They're A, D, and E are the 3. Let's talk about why that is. So A, this first carbon is not an asymmetric carbon atom because 2 of the 4 bonds that this carbon makes is 2 oxygen. But the second carbon is an asymmetric carbon atom. If we look at the 4 bonds that this carbon makes, this is one group of atoms that it bonds to. This is the second group, third group, and fourth group. Those 4, none of them are exactly the same. And so that's what we consider an asymmetric carbon atom. And so what can happen is that we can switch the left and the right side, and they could be mirror images of one another. Like if we switch these, the top and bottom stays the same. All right, that's why A is. Let's look at D. So D, here we have, let's look, this first carbon is not an asymmetric carbon atom because 2 bonds are going to the oxygen, but this next one is. We look at here, 1, 2, 3, 4 different groups of atoms, and so that's the rule, and we could switch the left and the right side, and we would have a mirror image of it. So this could have a mirror image isomer. And lastly, E, this is also an asymmetric carbon atom here, where we have 4 different groups of atoms, and that could also, if we switch to have an enantiomer. That's the 3 there. So that one was difficult. All right. So let's look at I think the rest of them are a little bit easier. So number 4, the carboxylic acid. So in looking at this, carboxylic acid, you should think back, okay, that's something that has the carboxyl group. Then you have to think, what does the carboxyl group look like? In your head, can you think about what the carboxyl group looks like without looking back at your notes? This is what you need to be able to do. So carboxyl group, you should say, okay, what am I looking for? That's C with a double bond to an O and an OH. So that's what I'm looking for. So then you go through and look at your different molecules that's looking for that group, and we find that only on letter E. So if we look at E right here, this is the carboxyl group, C with the double bonded O and the OH. I want to point out, very common mistake is people writing either D or A, because look at D, has a C with a double bonded O, but notice here that second bond coming off of here is not an OH, it's just an H, so that's not a carboxyl group. Same thing with this one, all right, so that's a common mistake. Number 5, can make a cross-link in protein. So, all right, so then that's the function, so you have to go back and think, okay, what you guys probably did is looked at some cross-link in protein, went to your notes, looked to see which one said cross-link in protein, and said, okay, this is the functional group, it's the sulfhydryl group, it looks like an SH, and found the SH. But what you need to be able to do, when I said you have to commit to memory that the chart and the functional groups, is you should be able to read through this and say, cross-link in protein function, what functional group is that? That's the sulfhydryl. What does sulfhydryl look like? It's an S bonded to an H. Let me find an S bonded to an H. So you have to kind of go through that in your head, that thought process in your head, without looking at anything. And so there, the SH is right here, so that's also on molecule E. Okay. So then hydrophilic, number 6. Hydrophilic means it's water soluble, so it has polar parts to it. So basically, for hydrophilic, if they have our functional groups, polar functional groups, the only functional group that's not polar that was in our chart was the methyl group, not CH3, but all the other functional groups, the hydroxyl group, the phosphate group, and so on, all of them are polar, which makes the molecule hydrophilic. So therefore, any molecule that basically has these functional groups on it, besides the methyl group, is hydrophilic. So what molecules are that? So A, is A hydrophilic, do you think? Yes, A is. How about B? No, B is just made out of carbons and hydrogens. That's non-polar bond, and therefore non-polar would be hydrophobic, not hydrophilic. C. Should we put C here? Yes. D. Yes. E. Yes. F. No. All right, and so that is what we should have there. So that brings us right to number 7, hydrocarbons. Hydrocarbons are made out of just hydrogen and carbons. These guys are non-polar, hydrocarbons are. And so that is B and F, the two that we didn't write in the previous one. 8, amino acid. Amino acid, you should remember, has, looking at the name, has an amino group, and then why it has acid in its name, what functional group gives it the molecule acidic properties? We already talked about it up here. It's this one here, the carboxyl group. So what you're looking at for an amino acid is having the amino group, and so you have to know what these look like. The amino group is NH2. The acid is the carboxyl group that looks like this. See, with a double bond to the OH. So you're looking for a molecule that has both of those together, and that is molecule E. Number 9, organic phosphate. That's the name of molecules that have the phosphate group. Phosphate group is PO4. And so when we look at that, that is, here's one phosphate group, so we have molecule A. And what else? C, right? It has the phosphate group. All right, 10 and 12, let's do that together, those two together. Can somebody tell me why 10 and 12 are related?
They're both in the same carbon.
Yeah, they both have the carbonyl group, a C with a double bond to an O. What makes them different is that the aldehyde, that carbonyl group is at the end of the molecule. Ketone is in the middle. So when we look at aldehyde at the end, we actually have 2 of those. We have A right here. This is a carbonyl group. It's not the carboxyl group because it would have an OH here, so it is a C with a double bonded O. So A is the one answer there for the aldehyde. The second answer for aldehyde is D, because right here is the also at the end of the molecule. Whereas going to a ketone in the middle, that would be letter C, where it has this in the center. And then lastly, an amine. An amine is a molecule that has the amino group NH2. So the only one is that amino acid down here. There's the NH2, which is the letter. Any questions on that? All right, so hopefully if you had questions, they were answered. If not, please come see me before or after school. Yeah.
Could you repeat number 12?
Okay, so a ketone has the carbonyl group in the middle of the molecule. And so the carbonyl group is the C with the double bonded to O. So C here, you see how this C with the double bonded O is in a center carbon atom. It's not at the end of the molecule like these two.
Yes.
This is at the end. So we call that a ketone. So this molecule, just as a classification, has the carbonyl group, but it's called a ketone. Okay. And these two have the carbonyl group that are called aldehydes. All right, so they're just named differently. Any other questions? All right. And so, I kind of tried to model the thought process there. So as I said, you should be able to do that off the top of your head. So you could go on the companion site for the textbook and do some practice problems and practice questions and stuff like that to help you to see if you kind of get that. You have to commit that to memory. All right? Alrighty, so we're going to continue on with carbohydrates in our note. Switch gears here. Alright, so I think I gave you some generic information about how macromolecules are made. So remember, I went through this, just a quick little recap from the long weekend here we've had since Friday. So remember, we talked about macromolecules being either made or broken down by dehydration or by hydrolysis. And remember, they add or lose a water molecule to either form the bond or break the bond. And so we're going to look at that in each class of molecules that we look at, and we'll see it in action. And so carbohydrates was our first type of molecule, and that was first type of macromolecule. And we talked about sugars. Did we look at this? No. All right. All right. So this is where we literally at the very beginning. Okay. So carbohydrates. There are two purposes: fuel and building material. So they include sugars and chains of sugars. That's what polymers of sugars is. The simplest is monosaccharides. Mono means one, saccharide is another way to say sugar. So monosaccharide is one sugar. And the macromolecules is hooking all those monosaccharides together and forming polymers. And that the polymer for carbohydrates is called a polysaccharide. Poly means many, and saccharide referring to sugars. So the monosaccharides here, these guys are the monomer of carbohydrates, meaning that to make other, if it's not a monosaccharide, then you have to hook monosaccharides together to make let's say a polysaccharide. Remember, monomers are put together. I used the analogy of the train was being the polymer and each individual car being the monomer, and so the monosaccharides are the monomer for carbohydrates. So let's look at the very simple monosaccharides first. Monosaccharides have, and all carbohydrates are made out of just carbon, hydrogen, oxygen, but they are, for simple sugars, they're in a specific ratio, a 1 to 2 to 1 ratio for carbon, hydrogen, and oxygen, meaning that there's twice as many hydrogen as there are carbons and oxygens. Glucose is the most common monosaccharide, and we're going to talk in this class at length about glucose in many different chapters. It's very, very important. Anybody remember off the top of their head from bio the formula for glucose? I hear mumbling. Anybody want to, Megan? Yeah, C6H12O6. Notice that follows that 1 to 2 to 1. There's twice as many hydrogen as carbons and oxygens. And so different monosaccharides are classified by where their carbonyl group is. All right, so a little test for yourself. Carbonyl group. What does it look like? Colby? All right, double bonded to an O, and oftentimes also having an H there. And so, and then the carbonyl group in where that's located, as well as how many carbons long it is. So glucose, for instance, has 6 carbons, but not every monosaccharide does, which is what the next picture is showing you here. So this is showing you the variation. So, so we have 2 rows and 3 columns here of to classified. So this, the triose, the pentose, and hexose. Ose on the end of something refers to sugar. So when you see ose at the end of a name, you can be pretty confident that that's some type of sugar. So the tri meaning 3, so you can see here that this is 3 carbons long, 5 carbons long, and 6 carbons long, which there's a typo here. This would be 6. All right, C6. And so we see here, here's glucose. And we just looked at here. So that's that classification. So that's the first thing, is the length of the carbon, and then the rows are referring to where the double bonded oxygen is. So notice here we have the double bonded oxygen here at the end. At the end, this carbonyl group at the end, these molecules would be aldehydes, and that's why it says aldoses. Ald is referring to the aldehyde, that the carbonyl group, and ose is referring that it is a sugar, and so that's why it says that. And then ketoses here, these guys, their double bonded oxygen is somewhere in the center of the molecule, not in at the end, and this is referring to them that these are ketones. Well, that's why they're called that. All right, so these are different monosaccharides. If we look at these hexose sugars, these guys have C6H12O6. All of these guys do, glucose, galactose, and fructose. So therefore, they are what of each other? These guys are isomers of one another. So all of these are isomers. These guys, these 2 are isomers, and these 2 are isomers. So what they're showing you here, is what's highlighted here, is just these guys flipped, the hydroxyl group and the hydrogen, and that's the only thing different. And so this is actually, so these 2 are isomers of one another, and they're mirror images of one another, so they would be enantiomers. So the job of monosaccharides is twofold: fuel for cells and as raw material for building molecules. We'll touch on this a little bit more later. And the picture we just saw, where all of those monosaccharides were drawn in a linear format, as a linear skeleton. But what happens when they are in an aqueous solution, which means a water-based solution, which is what living things are, cells, and cells are bathed in water-based solutions, what they do is they form rings. And that's what this picture here is showing you. For this class, we don't need to know how the formation of the ring occurs. This is the linear format, but this is what the ring looks like. And so from now on, when we look at single sugars and monosaccharides, you'll see them in the ring form, and that's probably what you saw in biology when you saw glucose is in the ring form. And so that's what this is showing you here. Sometimes our textbook will shorthand the ring form and not put the carbons, and not, so each one of these little points here represents a carbon. And notice the 6th carbon is off, not as part of the ring. So that's what we'll see here from now on with carbon rings. So that's your monosaccharides. So what happens is that another classification of a carbohydrate is putting 2 of those monosaccharides together to form a disaccharide. Di meaning two sugars, and so dehydration reaction joins them, and they have a special bond. They call it a glycosidic linkage, and that's what we see here. And so, did I go too fast? Am I good?
Yes.
Oh, yeah. Picture is going to show, like I just reviewed the purple circles, the generic picture of making and or breaking down large molecules. This is going to show that specifically to making a disaccharide. So here we have, good, right? All right. So here we have 2 examples, A and B, making 2 disaccharides, maltose and sucrose. So maltose is hooking together 2 glucose molecules. So there's this 2 monosaccharides here. So when they come together, remember an OH comes off of one and an H comes off of another, and we lose a water molecule. That's the dehydration part of it, losing that water molecule. Now this oxygen and this carbon is not bonded. It doesn't have, the carbon doesn't have a 4th bond, and this oxygen doesn't have its 2nd bond. So these guys are going to bond to one another. And so what happens is this right here is the new bond. All right, that's your glycosidic linkage. They're now hooking those together, and that water molecule, we can write, if this is truly a reaction, you're going to have water as a byproduct there. And this is now a disaccharide made out of 2 monosaccharides. And then this is just showing you the glucose and fructose make a different molecule called sucrose. This is our regular table sugar. So the same process occurs, OH and H. And where's the new bond here? It's going to be right here. Okay, and so that's the new bond between the 2, and that's our sucrose molecule. So that's how they're made, and using dehydration. When we eat table sugar, sucrose, we cannot use sucrose in its form as 2 monosaccharides hooked together. So when we eat table sugar, what we do is our enzymes in our digestive system aid to break this bond to make them back into glucose and fructose, because what our body can only use the simple sugars. Our cells can only use the simple sugars. So a disaccharide is too big of a molecule to get through the cell membrane of our cells. So we can't use disaccharide, or we're going to learn next about polysaccharides. They're way too big. So our body, it's the whole purpose of your digestive system is to break molecules down back into their monomers, and those are small enough to be used by cells. So when you eat sucrose, our enzymes will break this down, and our enzyme will do what's the process by which we break it down or break this bond?
Digestion.
Well, it's going to happen during the digestion process. How does, what I'm getting at is what's the role of water? Yeah, hydrolysis. And hydrolysis is to use, hydro means use of water, lysis means to cut, so we're going to actually cut the bond here by adding water. So we're going to do the exact opposite. We're going to add, that we did here, we're going to add the H and the OH, and then it'll break down into glucose and fructose, and then we can use those sugars for energy and so on. And so we're going to hit on that a little bit more as we go along. All right, so that's your disaccharides. And then we jump inside. So we go from 1 sugar to 2 sugars. Now we're hundreds of sugars long. So very, very big molecules now. polysaccharides. The polymers of sugar have both storage and structural roles. So we're going to look at those two categories. Structure and function of a polysaccharide are determined by its sugar monomers. What kind of sugar is it made up of? And the positions of the glycosidic linkages. So how those bonds between the monomers work. So we're going to look at the storage polysaccharides first. So storage polysaccharides. Starch is an example. Made only in plants, and so it consists of entirely of glucose molecules. It's a chain of glucose molecules. And they store this chain of glucose molecules, the starch, in granules within organelles like the chloroplast inside their cells. And, whoops. And so that's what this picture here is showing you. This is, so each one of these little rings here represents a glucose molecule. So it's a chain of glucoses, and you can see that they spiral. Some of this has branching and so on. These two are types of starch. For our class, you don't need to know the different types of starch there. You don't need to know those names. But that starch is a chain of glucose molecules. So what happens is in plants, when plants make their glucose, because plants don't eat. We get our glucose by eating. Plants do not eat. They make their own glucose. Do you guys remember what process plants make their own glucose through, I should say? Photosynthesis. So they make their own glucose through photosynthesis. The reason why they make their own glucose is for energy. Glucose is a main energy molecule. And so they use some of that glucose right away to grow and so on and to stay alive, to do some chemical reactions and things like that inside the plant cells. So they use it to sustain life. But then they also make excess glucose. And so all the excess glucose that they make that they don't need currently to actually stay alive, they store it by putting them in chains. So they take all these excess glucose molecules and make these different starches, and they store them for later use. And so, for instance, like the potato plant, the potatoes are underneath the ground. That potato plant is a whole bunch of starch for that particular plant, storing excess starch and excess glucose in there. Think about this. Some bulb plants, like tulips, tulip bulbs come up, they sprout, and you get tulips in the spring, right? So what happens is the tulip comes up, you get the nice pretty flower, and it has its leaves. The flower dies off. You are not supposed to cut back the leaves. You're supposed to let the leaves die on their own, because what's happening is those leaves are capturing sunlight. The plant is doing photosynthesis, making glucose to stay alive, but also it's storing a lot of that glucose as starch, and guess where it stores it? Down underneath the ground in that bulb. So all the time where the tulip is not blooming anymore, but it's capturing that energy, it's making glucose and storing it as starch in the bulb, and then eventually those leaves die off. Then you can get rid of them after they're dead, and that bulb stays under the ground all through the summer, through the fall, through the winter, and then when this ground thaws and the temperature starts getting warmer, that temperature change triggers the cells in that bulb to start dividing again and a new tulip plant to grow. But where does that tulip plant get its energy? It's underneath the ground. It's not doing photosynthesis. It's relying on the glucose that is stored in long chains of starch underneath the ground. It's going to use that for energy until that tulip reaches the air, and the leaves come out, and now the leaves can do photosynthesis, and then it can grow, and so on and so forth. It needs that energy in the bulb to do that. So if you cut your tulip plants down right away after they bloom in the spring, you may get they may not come up again the next spring, or be very, very small, all right? Or sometimes they'll come up and never even reach. If you dig them up, you'll see that they have started to grow, but then they never reach the ground either, and that's because it may have run out of energy, all right? And so, so that's an example of plants storing their excess energy as starch. Now we don't store our excess glucose as starch. We store it as a molecule called glycogen. Glycogen is a storage polysaccharide in animals like us, and where we store our glycogen is in our liver and our muscle cells. So glycogen is very similar to starch in plants. It's long chains of glucose, but you can see here it's a much more highly branched, more complex molecule than starch. So I'm going to put here more highly branched and complex than starch. All right, so I'm going to draw a little. I'm going to move my little over here. I think it keeps automatically turning off. Hold on. To figure out why it's automatically. Here it's not on. There we go. And so I'm going to draw on the board here the relationship between starch and glycogen as it relates to us. And so, here's starch. Starch is in plants, right? And it's their storage. And they're hooking a bunch of glucoses together and so on and so forth. So a bunch of glucose molecules. All right, so they can, to use it later on, they can break the bonds between the glucose molecules and use the glucose for energy. And so that's the purpose for the starch in plants. Let's relate this though to us. So could we use starch in plants? The answer is yes. We've all eaten potatoes, right? Potatoes, you're eating the starch, okay? So when you eat the starch, so when it enters, so for us, when we eat the starch, it's a chain of glucose molecules. Remember, it goes through our digestive system. We can't use glucose in this format. This is way too big of a molecule. The glucose can't get into our cells. So what do we do to the starch when we eat a potato? We break the bonds between them. We have enzymes that break these guys here. We break the bonds by doing what? Adding water, right? So we're going to start breaking those bonds. So this is what happens when we eat the glucose, or eat the starch. It breaks down now into glucose. So instead of one big starch molecule, we have hundreds of small glucose molecules. Follow me? And so then what happens to those glucose molecules? So your digestive system's doing its work, it's adding water, now we have all these hundreds of glucose molecules. Those glucose molecules have to get to our cells of our body. How do you suppose that the glucose gets from your digestive system to the cell on your big toe? Do you have an idea of how it does that? Through your blood. So now, so you've just eaten this, so this is your blood vessel here. All these glucose molecules go into your bloodstream, and now your blood glucose levels go up. So now you have glucose in your bloodstream, and what happens is that glucose, the bloodstream goes to the highway system throughout your whole body, so this glucose is going throughout your whole body. The glucose does one of two different things. That glucose can be used for energy right away. So it can go in your cells. So let's say here's a cell right here. So it can go and enter the cells of your body and be used right away for energy. That's one thing that your glucose can be used for. The second thing is if you have too much glucose, let's say you don't need that much energy, but you've got all this glucose here, that's when the making of glycogen happens. So then the second thing is that it can be stored in your liver or muscle cells as glycogen. So let's say this is your liver cell. this glucose comes in and you're going to start hooking it together, and making glycogen. And the purpose of that is that we store that glucose for later, for let's say you fasted for a while, you haven't eaten. And so you don't have a high amount of glucose in your blood. And so what's going to happen is when you haven't eaten, the glucose that's going to trigger your low blood glucose level, triggers your liver to, and there's enzymes in there that will start and break down the glucose, the bonds between the glucose molecules, and take that glycogen and break it down and put glucose back into your bloodstream. And so that stays there in your liver and muscle cells where you can, at any time, when you need excess glucose for energy, you can break those bonds and put that glucose back into your bloodstream and use it for energy. All right, and so so that's a relationship between starch and glycogen and how we use them. All right, and so that's your storage polysaccharides, when you're really storing glucose or energy, your energy source. All right, so then there are two other polysaccharides, and they are under this category of structural polysaccharides. Cellulose is one. Cellulose is a major component of the tough wall of plant cells. So this is also in plants, but like starch, cellulose is also a polymer of glucose, but the glycosidic linkages differ. What's a glycosidic linkage again? This is a bond between monosaccharides. I'll just abbreviate there. So the difference is based on the two ring forms called alpha and beta glucoses. And this is where we'll stop for today, and I'll talk about alpha and beta glucoses tomorrow. The stuff you picked up today, just hold on to it. It's not homework right now, okay? So. Yeah.